Welcome to your simple science summary of FS Physics. This is really for you, the high-achieving 17 and 18-year-olds doing the IEB Further Studies Physics course here in South Africa.
That's right.
Today, our mission really is to cut straight to the core of analytical skills. It's the fundamental toolkit you need to really understand and, frankly, excel in experimental physics.
Absolutely. Think of them maybe as your scientific superpowers for navigating data, making sense of measurements.
Yeah, making sure your conclusions are rock solid.
Exactly. And look, this isn't just about learning rules for an exam. It's about building that critical thinking, that practical understanding. You'll find it indispensable in tertiary studies and, honestly, beyond.
It's the bedrock of reliable science, isn't it?
It really is.
So we've picked out 3 crucial areas for this summary today. We'll start with the universal language of SI units, then tackle the, unavoidable realities of uncertainties and significant figures.
Always present.
And finally, wrap up with the art, really, of graph analysis. How do these all kind of link together?
That's a great question, actually, because they really do build on each other. You can't properly talk about, say, reliable measurements or analyzing graphs if you haven't first agreed on a common language.
Oh, okay.
So SI units, that's our essential starting point. They make sure everyone, everywhere, is basically speaking the same measurement language.
Okay, right. Let's unpack that. I mean, imagine trying to build something really complex like, I don't know, a satellite.
Yeah.
And one team uses feet and inches, another uses meters. It'd be, chaos.
Total chaos. And potentially disastrous. Think about engineering tolerances. That's exactly why SI units are so vital. They give us that consistent global standard.
So when you measure something in meters here in South Africa, a scientist in Japan or Brazil knows exactly what you mean.
Precisely. It prevents those catastrophic misunderstandings. And the beauty of it, the International System of Units, SI, is that it's all built on just 7 base quantities.
Oh, he said.
Just 7 fundamental pillars. Everything else in physical measurement is derived from these. It's actually quite elegant.
So what are these 7 key players?
Okay, so we have mass, measured in the kilogram, length, that's the meter, time, in seconds.
Standard stuff so far.
Pretty much. Then electric current, the ampere. Thermodynamic temperature, that's Kelvin, not Celsius in the base units.
That's Kelvin.
Amount of substance, which you know from chemistry, the mole. And finally, luminous intensity in candela.
Candela, okay. Not one you use every day, perhaps.
Not unless you're in optics, probably. But those 7 are the irreducible foundation.
And from these, we build everything else, the derived units. Can you give an example?
Sure. Think about force. Force isn't a base unit, but remember Newton's second law? F equals ma.
Mass times acceleration.
Right. So the unit of force, the Newton, is actually built from base units. It's a kilogram times a meter divided by second squared, QGMS4. So you don't need a whole new fundamental unit. You construct it. It makes the whole system incredibly logical and consistent, like a language with root words.
Okay, and this is where it gets really useful for, checking your work. Homogeneity.
Yes. This is such a powerful tool. You can use the base units to check if your physics equation actually makes sense dimensionally, even before you plug in a single number.
Like a quick proofread for the maths.
Exactly like that. It's an error detector built into the laws of physics, almost. If you're working out an equation for, say, energy, and one side comes out with units of kilograms times meters per second.
Which is momentum.
Right. And the other side should have energy units, kilograms times meters squared per second squared. Instantly something's wrong. The dimensions don't match.
The equation isn't homogeneous.
Correct. It doesn't matter what numbers you use. If the dimensions are inconsistent, the equation is fundamentally flawed.
It's like a sanity check for your physics.
It absolutely is. And it has real-world consequences. Remember the Mars Climate Orbiter disaster back in 1999?
Vaguely. What happened there?
Well, essentially it crashed because one engineering team used imperial units, pound-seconds, for thrust calculations, while another used metric units, Newton seconds.
Oh.
And the conversion wasn't done correctly in the software interfacing them. A simple dimensional analysis, a homogeneity check, could potentially have caught that discrepancy.
Wow. A multi-million-dollar oops based on units.
Exactly. It really underscores how fundamental and, frankly, critical getting units right is.
Okay, so SI units give us our common language. But even with that perfect language, experiments aren't perfect. Which leads us straight into Uncertainties.
The unavoidable truth, yes. Every single measurement you make has some degree of uncertainty.
And it's not about being wrong, right?
Not at all. It's just about acknowledging the limits of your instruments, your methods, even you as the observer. Accepting and quantifying uncertainty is basically the language of scientific honesty.
Okay. And we mainly talk about two types of errors, don't we? Random and systematic.
That's right. Let's break them down. Random errors are those, well, unpredictable fluctuations, little variations around the true value.
Like static on a radio signal.
Good analogy. It's like the natural noise in an experiment. Maybe you're timing something with a stopwatch, you press it slightly differently each time, or there are tiny, unpredictable changes in the environment, or the instrument itself fluctuates slightly.
And these can go either way, too high or too low.
Exactly. They're unbiased. The key thing about random errors is, while you can't just wish them away, you can reduce their impact.
How do you do that?
By taking multiple measurements, lots of them ideally, and then averaging the results. Repeating the experiment helps smooth out those random bumps. It gets you closer to a reliable average value.
Like reading an analog scale. The uncertainty might be half the smallest division.
Precisely. Or, on a digital meter, it's often plus or minus the last digit shown. Taking several readings and averaging helps account for those tiny reading variations or fluctuations.
Okay, that makes sense. But then there are systematic errors. They sound more sinister.
They can be trickier, definitely. Systematic errors are consistent. They always push your measurement in the same direction, always too high or always too low.
So not random noise, but a definite bias.
Exactly. They usually come from a flaw in the equipment, like a scale that doesn't read 0 when nothing's on it. We call that a zero error. Or maybe it's not calibrated correctly, or it could be a flaw in how you're doing the experiment.
Like measuring something hot with a metal ruler. The ruler expands.
Perfect example. The ruler itself expanding would consistently make your length measurements slightly shorter than they really are. Or reading a volume in a measuring cylinder, but you're not looking at it from level, avoiding parallax error. If you always look from slightly above, your readings will always be a bit off in one direction.
And crucially, repeating the measurement won't fix a systematic error, right? If your scale always adds 0.5 kilograms.
Measuring it 100 times just gives you 100 readings that are all 0.5 kilograms too high. It doesn't average out.
It affects the accuracy.
Exactly. And this brings us right to that vital distinction. Accuracy versus precision. The dartboard analogy is the classic way to explain this.
Right, the dartboard helps visualize it. So accuracy is?
Accuracy is how close your measurements are to the actual true value. Are your darts hitting the bullseye?
And precision.
Precision is about how close your repeated measurements are to each other. Are your darts all clustered tightly together? They might be clustered tightly way off in a corner, mind you.
Okay, so you could have high accuracy and high precision, all darts tight in the bullseye. The dream.
That's the ideal, yes. But what if all your darts are tightly clustered together, really precise, but they're all over on the double 20?
So that's high precision, but low accuracy. You're consistent, but consistently wrong.
Exactly. And that often points toward the systematic error you haven't accounted for.
Then you can have darts scattered sort of all around the bullseye. Average position is okay, but they're spread out.
That would be a high accuracy, generally speaking, but low precision. Your method isn't consistent shot to shot.
And worst case, darts everywhere, nowhere near the bullseye. Low accuracy, low precision.
Right. Understanding this difference is so important for evaluating your data quality. It tells you what might be going wrong. A precise result looks good, but it could still be inaccurate due to a hidden systematic issue.
Okay, so we've got measurements, we understand the uncertainties, now we need to report them properly. That's where significant figures come in.
Precisely. Sig figs, as they're often called, are all about communicating how precisely you know a number. It's scientific honesty again.
Not claiming more certainty than you actually have from your measurement.
Exactly. You need to know which digits are significant. The basic rules are all non-zero digits are significant.
Easy enough.
Zeros between significant digits are always significant. Like in 703, that 0 counts.
Okay.
And the ones people sometimes forget. Trailing zeros after a decimal point are significant. If you write 5.00 meters, those 2 zeros tell us you measured it precisely to the nearest centimeter. Writing just 5 meters is much less precise.
Right, they indicate the level of precision. Right. What about zeros just used to place the decimal, like in 0.0005?
Those leading zeros are not significant, they just show magnitude. In 0.005, only the 5 is significant, but in 5.00, the 5, 0, and 0 are all significant. 3 sig figs.
Okay, and then doing calculations. This is where my students sometimes get tripped up. The rules for adding, subtracting versus multiplying, dividing.
Yes, they're different, which can be confusing at first. For adding or subtracting, you look at the decimal places. Your answer should have the same number of decimal places as the measurement with the fewest decimal places.
So it's limited by the least precise decimal place.
Correct. But for multiplying or dividing, you look at the total number of significant figures. Your answer should have the same number of significant figures as the measurement with the fewest significant figures overall.
Fewest sig figs limits the answer.
Got it.
And rounding.
Standard rounding rules apply. Round up if the next digit is 5 or more. Although there's a specific round to even rule for when the digit is exactly 5, followed by nothing or zeros. But often just rounding 5 up is accepted at this level. The key is consistency.
And the whole point is, again, honest representation of precision. Don't make your calculated answer look more precise than your weakest measurement allows.
Exactly. And this carries through when you combine uncertainties. When you calculate something using multiple measurements, their uncertainties combine too.
Right. We talk about absolute uncertainty.
Which is the raw plus or minus value, like -0.1 centimeter.
Fractional uncertainty.
Which is the absolute uncertainty divided by the measurement value, a ratio.
And percentage uncertainty.
Which is just the fractional uncertainty times 100, expressed as a percentage, useful for comparing the relative uncertainty of different measurements.
And how do these combine, sort of conceptually?
Well, the simple rules are, when you add or subtract quantities, you add their absolute uncertainties.
Add the values.
But when you multiply or divide quantities, you add their percentage uncertainty.
Add the percentages, right.
And if you raise a quantity to a power, say you square it, you multiply its percentage uncertainty by that power. So squaring doubles the percentage uncertainty.
That's important. Squaring something makes its relative uncertainty larger.
It does. Understanding this propagation of uncertainty is crucial for knowing how reliable your final calculated result is. And you can also calculate percentage error, how far your experimental result is from some known or theoretical value.
It all adds up to quantifying the reliability of your work. It's fundamental to being a rigorous scientist.
Absolutely. And a fantastic way to visualize these relationships and uncertainties is through graphs. Which brings us to our last skill. Graph analysis.
Graphs are just so powerful, aren't they? Much easier to see a trend than in a big table of numbers.
Oh, definitely. Our brains are wired for visual patterns. But for a proper scientific graph, especially in experimental physics, just plotting the points isn't enough. You absolutely need error bars.
Yes. Error bars. Tell us what they represent visually.
Okay, so error bars are lines drawn through your data points on the graph, and they visually show the uncertainty in that measurement. It's crucial to remember. The vertical error bars show the uncertainty in the y-axis value.
Up and down uncertainty.
And the horizontal error bars show the uncertainty in the x-axis value.
Left and right uncertainty. Okay.
The length of each bar, or half bar technically, tells you the magnitude of the random uncertainty for that point. A bigger error bar means a less certain measurement for that point.
So they tell the story of your data's reliability point by point.
Exactly. A graph without error bars is, frankly, incomplete. It hides really important information about how trustworthy your data is.
Now, often in physics, we try to get a straight line graph, right, by manipulating equations or choosing variables carefully. Why is that so useful?
Because straight lines are easy. We understand them mathematically really well. The equation y equals mx plus c is familiar.
Dependent variable y, independent variable x, gradient m, y-intercept c.
Right. And you can often rearrange quite complex physics equations to fit that linear form. This process of linearization is incredibly powerful. It lets you easily determine constants or check relationships.
So you plot your data with error bars, draw a line of best fit. How do you get the gradient m and the intercept c?
You calculate the gradient using 2 points on your line of best fit, not necessarily data points, but points on the line itself. Choose points far apart for better accuracy. The y-intercept c is simply where your line of best fit crosses the y-axis.
But wait, what about the uncertainty? If our points have uncertainty, surely the gradient and intercept derived from them must also have uncertainty.
Ah, excellent point. Yes, they absolutely do. And this is a really neat part of graph analysis. To find the uncertainty in your gradient, for example, you don't just use the best fit line. You also draw 2 other lines.
Okay.
You draw the steepest possible straight line that still goes through all the error bars of your data points.
Right.
And you draw the shallowest possible line that also goes through all the error bars.
Lines of worst fit? Kind of. Max and min slopes.
Kind of, yes. Maximum and minimum plausible slopes, given your data's uncertainty. The uncertainty in your gradient is then roughly half the difference between the gradient of the steepest line and the gradient of the shallowest line.
That makes sense. It gives you a range. And you do the same for the intercept.
Exactly the same principle applies to finding the uncertainty in the y-intercept. You see where the steepest and shallowest lines cross the y-axis. Half the difference is your uncertainty in C.
And that y-intercept C can sometimes tell you something important too, right?
Definitely. Sometimes C represents a real physical quantity, like an initial offset or a threshold value. You can compare your experimental C to a theoretical value. Other times, theory might predict the line should go through the origin. If your best fit line doesn't go through the origin, and the intercept is significantly non-zero, even considering its uncertainty.
It might point to a systematic error, like that zero error on the scale we talked about.
Precisely. It's a fantastic diagnostic tool built right into your graph analysis.
So ultimately, from this careful graph analysis, plotting points, adding error bars, finding the best fit, and the uncertainty in its gradient and intercept, you can derive real physical insights.
That's the goal. You might determine the value of acceleration due to gravity, or a spring constant from Hooke's law, or Planck's constant from the photoelectric effect data. You extract meaningful physics from your experimental numbers.
So when you pull it all together, these analytical skills, SI units, uncertainty, sig figs, graph analysis, they're not just separate hoops to jump through.
Not at all. They're completely interconnected. They form the bedrock of doing reliable, trustworthy experimental science. SI units give clarity. Uncertainty acknowledges reality. Significant figures ensure honesty. And graph analysis lets you visualize, interpret, and quantify the confidence in your findings.
And for you, tackling the IEB Further Studies Physics, really getting a handle on these concepts means you're not just plugging numbers into equations. You'll understand the why the units matter, why the uncertainty is there, what the graph is really telling you.
And that critical thinking, that deeper understanding, is exactly what prepares you for university-level science and, honestly, for critically evaluating information in the world around you.
It's about developing that scientific literacy.
Couldn't agree more.
Okay, so here's a final thought for you to maybe chew on. We've talked a lot about how even careful scientific measurements have inherent uncertainty. Knowing that, how does it maybe change how you think? When you see stats or facts reported, say, in the news or online, that often don't mention any uncertainty or margin of error, what does knowing these analytical skills make you notice?